Well, good morning. This is 11:36, 6 minutes late getting started for Math 237 linear algebra. I came in earlier, nobody was here, so I thought, well, I'll go down to the restroom and come back. Still nobody's here, so guess I'll get started without anyone being in the room, but I'll wait and do any announcements until at least one more body comes in. So let's go from current slide, which is here, and where we left off last time. We're on page, in chapter 2, matrices, 2.1 operations with matrices, and we're in the discovery at the top of, or near the top of page 44. And it says, let's make a couple of discoveries, okay? They give us two matrices. Let me get my pen set up. First of these is matrix A, and that's 1, 2, 3, 4, very creative matrix, 1, 2, 3, and 4. And matrix B is 0, 1, 1, 2. Okay, two matrices. It says calculate A plus B and B plus A. So A plus B, remember how to do this? It's been a while. Okay. You can only add two matrices as they're exactly the same size. These are. They're both 2 by 2, so you can add them. So you add element by element. 1 plus 0 is 1. 2 plus 1 is 3. 3 plus 1 is 4. And 4 plus 2 is 6. Okay? Then it says to do B plus A. And I think you know exactly how that's going to pan out, because addition is commutative, the elements are commutative. 0 plus 1 is 1, 1 plus 2 is 3, 1 plus 3 is 4, and 2 plus 4 is 6. So they are exactly the same. So matrix addition does appear to be commutative. All right, glad to see you. I hate talking to myself. Begins to make me doubt my sanity. Okay. So, Keyston's here. Let me get the projector turned on. And the light turned on. Also very conducive to falling asleep, so I'm glad you're here. Get the light on, a little noise. Okay. We're just doing the discovery near the top of page 44, chapter 2, matrices, 2.1, operations with matrices. But since I've got a live body here now, I'll go over the announcements. There aren't that many or major, but let me go over them. First and foremost, our volleyball team, which, by the way, had an incredibly successful season last year. I hope they're on the road to do one again this time. They are playing, let's see, today is the 19th. So they are leaving for Bevel State, Fayette, Alabama. They have a match at 6 this evening, so they'll be leaving at 2:30. However, one of my students in the thing said they were leaving earlier than that, so in my morning class, so they may have moved up the time. This weekend, or at least part of the weekend, Friday and Saturday, they're playing at LaGrange College tournament in LaGrange, Georgia. And so we wish them well there. If you happen to be over near LaGrange, stop in and watch them play, Friday or Saturday. Okay? LaGrange College, whatever that is, 2-year school, 4-year school, whatever. And then I'll wait till next week to read you the rest of these. Okay. Our College Scholars team, the Scholars Bowl team, is currently recruiting players with knowledge in any subject, including history, literature, science, music, current events, mythology, mathematics, everything. So if you're interested, contact Mr. Matthew West. He's the coach. He's in this building, on this hall. Go down half a flight of stairs. Go down in between the first and second classrooms on the left, 259 and 261. His office is in between. All right. I've got a phone number if you want to call them, email if you want to email them. The exhibition at the Birmingham West, Austin's Birmingham West Library will be running through September 23rd. It should be a really interesting exhibition, Darkness in the Life, Alabama Holocaust Survivors Through Photography and Art. There were 20 Holocaust survivors living in Alabama, and these are some memories that they posted. There was a program, but that was last Monday, so that's over with, so the exhibit's still there. And the NASA's Community College Aerospace Scholars Program will be accepting applicants through October the 16th. I've got the information here if you want to look into that. Okay, we're doing the discovery on page 44, chapter 2, matrices 2.1, operations with matrices. We just did, or I just did before you came in, adding these two matrices, A plus B, and then adding the reverse of them, B plus A. The question is matrix addition commutative? Okay, notice they're the same matrices. I think you can argue and you could prove it if you're into making proofs. They are indeed commutative, because when you add two matrices, they have to be the same size, but when you add two, you're adding this element to this element. And since the addition of the elements is commutative, the addition of the matrices are commutative also. So they are. Now it says calculate AB. That's the product of these two matrices. Now, can you multiply those two matrices? Yeah, that's a 2 by 2 times a 2 by 2, and that sure will work because these two inner 2's are the same, and your answer will be, guess what? A 2 by 2. So let's multiply those two. First entry is the 1, 1 entry. Row 1 of A, column 1 of B, multiply those, and what do you get? What's that? Yeah.
I was thinking about something.
2. The first row, second column, that would be 5. Perfect. Second row, first column would be 4. And second row, second column would be, say again? Okay, 3 plus 8 is 11, right. Okay, sorry, I don't hear well. Now let's try BA, the multiplying in the different order. Now, of course, that's still doable too. I'll just put A on this side. Okay, and that's 1, 2, 3, 4. And it's still a 2 by 2 by 2 by 2. And for some reason that disappeared. And this one now is good. These two are the same. You get rid of them. So you get a 2 by 2. 1, 2, 1, 2. Let's do those. The 1, 1 entry is 0 times 1 is 0 plus.
Oh, wait, no.
You said 3? Yeah, 3. And you can see right now they're not invert. They are not commutative. But let's continue. The 1, 2 entry would be 4. The 2, 2 entry, 2, 1 entry, sorry, 2, 1 entry would be 7. And the 2, 2 entry would be 10. Nowhere close, okay? So, is multiplication commutative? You can definitively say no. Now, just because those two happen to goodness, what happened to my entry there? It just completely disappeared. This is also a 6 here. Okay. I don't know where that went. Just because these two would add and you got the same, you can't definitively say addition is commutative unless you think through it and say, well, yeah, because you're just adding elements together, and since the addition of elements is commutative, the addition this two. But multiplication, no, because you're multiplying row-column stuff, and that's going to change when you reverse the order of those things. So for sure, the multiplication is not commutative. All right, I think we're ready for example 5, which is a bunch of matrices, isn't it? All right, let's see. I hate they do all the work for you. I don't know what they were expecting you to do, but I'm not going to do the work for you since you don't have a book. We're going to do it from scratch. 1, 0, 3, 2, negative 1, negative 2.
I got the book.
Oh, you do have the book. E-book.
Yeah.
Yeah, okay. So, yeah, you can see the answer. Shame, shame. Okay. Negative 2, 4, 2. 1, 0, 0. And negative 1, 1, negative 1. Can we multiply those two? Why?
Because,
2 by, what's the size of the first one? 2 by 3, and this is a 3 by 3. And since the middle two are the same, you know your answer's got to be a 2 by 3. Okay? So it's going to be 1, 2, 3, 1, 2, 3. Okay? The 1, 1 column is going to be, entry is going to be, second? Oh, you already did it? Are you reading it off of it? Huh?
yeah, I read it out.
Yeah. Let's make sure they got it.
They already had worked that out.
What's that?
What you was talking about, they already have
Yeah, they already have done everything for you, so why make it an example? I don't know. But let's just do it quickly. Negative 2 plus 0 minus 3 would be minus 5. Make sure they did it right. That's a 4 there. That's an ugly looking 4, but that's a 4. So that would be 4 plus 0 plus 3 is 7. Hope they got it. And 2 plus 0 minus 3 would be a minus 1. Right so far? Yep. Next would be negative 4 minus 1 is negative 5, plus 2 is minus 3. The 2, 2 entry would be 8 plus 0 minus 2 would be 6, and 4, 0 plus 2 would be 6. Did I get it right? Yes, they did. Good for them. All right. The B is a little bit interesting, so let's do it. 2, 3, 4, negative 2, 5, negative 2, 5. I can't walk and chew bubble gum at the same time. 1, 0, 0, 1. What does that equal? Can you even do it? Yeah, 2 by 2 times a 2 by 2 gives you a 2 by 2. Okay, so 1, 2, 3, 4. So let's do it. What you get? 3 plus 0 is 3. The 1, 2 entry would be first row times second column. 0 plus 4 is 4. 2, 1 entry would be second row first column. Negative 2, 0 would be negative 2. And 2, 2 entry, second row second column, 0 plus 5. And what do you notice that is? Yeah, that's the same as this. And the reason is, we haven't named that yet, have we? But you know what it is.
Yeah.
What is it called? The identity matrix. The identity matrix is any square matrix, has to be square, with ones down the main diagonal. Everything in the main diagonal is a 1, and everything anywhere else is a 0. That's an identity matrix. And when you multiply any matrix that's multipliable by an identity matrix of the proper size, you'll get the very same matrix you started with. And that's because it acts like the number 1. Identity element in addition is 1. The identity matrix in matrix multiplication would be, if it's the appropriate size, the square identity matrix. Okay. Now, C is also interesting for another reason, and it's nothing we can really harp on too much now, but I just wanted to let you know. 1, 2, 1, 1 multiplied by negative 1, 2, 1, negative 1. Let's multiply those two. Can we multiply those two together? Sure, it's a 2 by 2 times a 2 by 2. The middle 2's go out, enabling you to multiply, and the answer will be a 2 by 2. Okay? So what's the first row, first column? Minus 1 is 1. First row, second column is 0. And second row, first column is 0. And second row, second column 1. Whoa, what do we get here? The identity matrix. Now that tells you something about these first two matrices that we don't know what it's telling you yet. Do you know what it is? Because you've had it before?
Yeah.
What do you know about those two then?
Remembering correctly, it's a matrix that acts as an element for an operation.
Okay. Now, yeah. Okay, I think I know what you're talking about here. The word I'm looking for, they're inverses of each other. Yeah, they're inverses of each other. Anytime you multiply two matrices together, of course they have to be square. I think, I'm pretty sure they do. Then, and you get the identity matrix, that means those are inverses of each other. Okay? Now, later we'll learn a real easy way to check to see if two 2 by 2 matrices are inverses of each other. A real handy-dandy way of doing it, but we haven't gotten there yet, so we'll get there later. Okay, so I jumped the gun on that one. I shouldn't have told you, but they are indeed. Now here's sort of an interesting one. What do you have here? 1, negative 2, negative 3 multiplied by 2, negative 1, 1. First, can you even do that? What you got? One by 3 multiplied by a 3 by 1. The 3's are the same, then you can multiply, and your answer is going to be a what? 1 by 1, which means it's a single digit. And sure enough, that's all you get. What do you get? Yeah, 2 plus 2 is 4, minus 3 is 1. Now, it's not the number 1, it's the matrix 1, okay? But that is just the number 1, it's all that's in there. But if you're multiplying matrices, you get a matrix answer. Okay? Well, would that work if you did it the other way? If you did a 2, negative 1, 1 multiplied by a 1, negative 2, negative 3. You think these two could be inverses of each other? Because the first one gave you the identity matrix. You can't get more identical than that. No, they have to both be square matrices. These are not. What were your, can you multiply these two? What is it? 3 by 1 multiplied by 1 by 3, and guess what? Whereas before you got a single, now you get a 3 by 3. And let's do the entries. The 1, 1 entry is just what? Two. The 1, 2 entry is negative 4. The 1, 3 entry is negative 6. The 2, 1 entry is negative 1. 2, 2 entry is 2. 2, 3 entry is second 3. Okay. And the 3, 1 entry is 3, 2. 3, 3. Okay. So lo and behold, you wind up with a big old 3 by 3 matrix, which was some of the easiest multiplying you ever do because you didn't have to remember what you added to. They just were single digits every time. Okay. So, yep. I hope that's what they got. They better have. Yep. Looks the same. Okay. Now, we're going back. Okay? Going back to what? Going back to systems of linear equations. Wait, I thought we had this not. Well, we sort of do. But this is just going to show you another way to do it. But that means I have to write all this stuff out. Well, you got it in your book there, right? Okay, so you see it's A11x1 plus A12x2 plus A13x3 is equal to B1. We've seen this before. A21x1 plus A22x2 plus A23x3 is equal to B2. And A31x1 plus A32x2 plus A33x3 is equal to B3. Okay? Now, remember how we did it before? We wrote it as a adjoint matrix. So is that what we call it? Yeah. Augmented matrix. Okay? We're not going to do that now. What we're going to do now is this. Write that as a matrix A11, A12, A13. Hey, that's the same as what we did before, but we're not going to augment it. We're just going to write that. A21, A21, A22, A23, and A31, A32, A33. Okay? And multiply that by the column vector x1, x2, x3. And that will yield the constant vector b1, b2, b3. Now basically all we did there is translate a system of equations into a matrix multiplication problem. And we can check this pretty easily and see that indeed is true because we know that A11x1 plus A12x2 plus A13x3 is B1. That was our first equation up above. The second equation was A21x1 plus A22x2 plus A23x3 is B2. That's right. And A31x1 plus A32x2 plus A33x3 is equal to B3. That's exactly the system of equations we had. So why did we do that? Well, they're not telling us yet, okay? But what we're going to do is figure out a way to fiddle with this differently from our augmented matrix, which we did before. Fiddle with this and come a different way to solve for the x1, x2, x3. Okay? And I think you know where we're heading because you probably had it before, but let's see what we've got. Now, we're going back in time here and do it the old way first. This time they say, solve this matrix equation. Now, this is a different one, so I'm going to erase that one. I don't think I need the room, but just so you won't get it confused. Okay? It says, solve the matrix equation AX, x being a vector, is equal to 0 being the 0 vector. Okay? We've already done things like this before, but this time the matrix A is 1, negative 2, 1. 2, 3, negative 2, and the x vector had better be an x1, x2, x3. Got to be, because you have 3 columns here, you need 3 rows there. Okay? And the 0 vector, so this is A, here is the x thing, and of course the 0 vector is just 0, 0, 0. Okay. Now, how we did it before was augmenting the matrix. Almost 1, negative 2, 1, 0, 2, 3, negative 2, 0, and row reduce. Well, first thing we want is a 1 right there. We got it. Good deal. What do we want next? A 0 below it. How do we make that happen? Negative 2, row 1, plus row 2 is the new row 2. So that will produce you write down the first one, 1 minus 2, 1, 0. And then you get 0, 7, minus 4, and 0. Okay? Now, what do you want to happen next? A big boo hiss here. Okay? What you want next is, you got a 1 here, 0 below it, you want a 1 there. Now, there's no good way to make that become a 1. Okay? So, basically what we have to do is, well, there is a good way, as good as any way, but only one way, and that's divide by 7, which makes for a real pain in the neck problem. So we'll do row 2 divided by 7 is the new row 2. I'm just going to divide by 7 here, divide by 7 here. All right, so our new row 2, we've got a 1 minus 1, minus 2, 1, 0, and we got a 0, 1, minus 4/7, 0. Okay. Now, what do we want to happen next? Review. We got a 1 in upper left, that's what we want, 0 below it. Got 1 as the first non-zero entry in the second row. What do we want next? Negative 2 to become a 0. How do we make that happen? 2 times row 2 plus row 1 is the new row 1. Okay? So let's make that happen. We're keeping the second row, 0, 1, minus 4/7, 0. All right, so let's do what it says. Minus 2 times 0 plus 1 is 1. All right. Do the same operation. Sorry. Man. Okay. 2 times 1, 2 plus negative 2, that's a 0. Now the fun one. Okay. What does this give us? Negative 8/7, right? Plus 7/7 is negative 1/7. And then I can do the last one. 0. Okay. That's so easy. What does that tell us? X of 1 is equal to, or if you wanted to write it more explicitly, x of 1 minus 1/7 is equal to 0, which implies that x of 1 is equal to negative 1/7. Say again? I'm sorry, I can't hear.
There's 3 variables.
Yeah. Oh, yeah. Sorry. Yeah. I was in outer space or something, I think. Okay, let's start this over. Okay. You're right, there's 3 variables. We've got to deal with that first. Okay. 2 of these we can solve for. This one we can't, so we choose a parameter. What parameter do you want to have? Second t. Let t equal x of 3. Okay, or x of 3 equal t. Now this one says for us x of 1 minus 1/7 t, because that's x of 3, is equal to 0, which now implies that x of 1 is equal to 1/7 t. You add that to both sides. Okay? And then the second one implies that x of 2 minus 4/7 t is equal to 0, which implies that x of 2 is equal to 4/7 t. Okay? So our solution set, you might want to call it, is a set of all points that fit this bill. 1/7 t, comma, 4/7 t, comma, t. Now that's a little, in some ways, sort of awkward seeming because of all these fractions in there. You can multiply everything in there by 7, right? And you get t, 4t, 7t. There's another way to express your any ordered pair you want to have, you can express that way. Now, obviously, because this is a homogeneous or homogeneous equation, what's the solution does that always have? Trivial solution. Does 0, 0, 0 work for those? Absolutely. That t equals 0, everything's equal to 0. Okay. So that is a solution because it's got to be. And then these are all the other solutions you have. And you can phrase them either way you want to there. I think the book they did the second way. T, 4t, and 7t. Okay? Just a little bit easier. Nicer on the typesetter too. They don't have to do all the fractions. Okay. Now, you can write then your solution set. I wrote it as a ordered triplet. Since they originally had it this way, you could write it this way. T, 4t, 7t. Okay? That's your x1, x2, x3. Because that's how they've written it here. Which, you can rewrite that as 1, 4, 7, all multiplied by t. Okay? So there's another way to write it. They wrote the t in front. I'm not really sure why, but it's perfectly fine. where T is any scalar in the world. 45 fifths. Well, that's 9. 47 fifths. That would be fine too. Negative pi thirds. It doesn't matter what T is. Any scalar. Okay. So any scalar multiple of the column matrix is a solution. Sorry. So they just give a few of them. 1, 7, 4 would be a solution. 2, 8, 14 would be a solution. 0, 0, 0 obviously is a solution. Negative 1, negative 4, negative 7 solution. That infinite numbers. Just keep putting in different T's. You got it. All right. Now something we talked about a little bit and then dropped. We're going to talk about it a little more and basically drop it again. But, you know, it can be done. Not dropping it completely, but it can be done. And these are partitioned matrices. And I'm hoping the reason that it just seems like we're picking it up, dropping it, picking it up, dropping it, is that it's pretty obvious stuff, and we may be using it later without thinking, oh, we're partitioning the matrix, because we're actually using it. Okay? So let's do a system again. A, X equal B. X and B are vectors, column vectors. A is a matrix that makes it work. So that matrix can be represented in a more convenient way by partitioning the matrices A and X in the following manner. Okay? Well, I guess we have to write them out. I was hoping not to. Matrix A is, and they really shorten it some, A11, A12, dot, 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 A1N, I believe they use. Yeah. A21, A22, dot, 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 A2N. A3N, oh no, they dot, dot, dot. Okay. I'm used to doing at least 3. They're shortening this considerably. Dot, 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 down to A M1, A M2, that's the dot, 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 2, dot, 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 everywhere, dot, dot. A sub Mn is the last entry they have. Okay. Now, sorry. It happens about the same time just about every day. That's when I've been staring at the screen, and I think I get right above the fan here, and it just dries my eyes out like crazy. Okay. So there's your matrix A. Your vector X is X sub 1, X sub 2, dot, 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 down to X sub N. Okay? Because this is an M by N matrix. This has to be an N by 1 row. Okay? It has to be an N there. Okay? But then your B, vector B from your, that's also a vector, and that's B1, B2, dot, 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 down to B sub M. Because you have M rows, you have to have an M by 1 at the end there. So you have an m by n times an n by 1 gives you an m by 1. These look sometimes like they have to be the same size. They're not. One's a 1 by n, the other's a 1 by m. Okay? So don't think they have to be that. Okay? Now, if you were to take matrix A and multiply it by the vector x, excuse me, goodness gracious, here's what you get. Now, this is a lot of writing, and you almost feel like it's just redundant, but there is a point here, okay? A11, A12, dot, 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 A1n, A21, A22, dot, 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 A2n, the writing is terrible. It's supposed to be an N, and it came out really ugly. Okay, there it is. And then we have a dot, 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 A sub M1, dot, 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 A sub M2, and everywhere, dot, dot, A sub Mn, there's a dot, dot, dot here and a dot, dot, dot there. I didn't put that one there, okay? Oh, man. Oh, yeah. Okay. X sub 1, X sub 2, dot, 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 X sub n. When you multiply those together, here's what you get. A11 X sub 1 plus A12 X sub 2 plus A13 X sub 3 plus dot, 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 plus A1 sub n X sub n. And that's equal to B1. Well, they just put the vector B over here, so we're not going to this. I don't know why, but they do. The next row, of course, is going to be A21 X sub 1 plus A22 X sub 2 plus dot, 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 plus A2n X sub n. And this is all equal to the matrix B. Okay? Dot, 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 A sub M1 X sub 1 plus A sub M2. Goodness, that's working. My writing's just getting awful. This pen is sort of draggy today. I think what I've done, I've erased so many times, I've got little wrinkles or ridges or grooves or something in the thing, so it's not doing well. A sub M2 X sub 2 plus dot, 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 plus A sub M n X sub n. Okay? And you have a dot, dot, dot up here, dot, dot, dot here, dot, dot, dots everywhere here. Okay? And that's equal to B. Now, all this is so they can get at this. Notice this first column here is X sub 1 times A11, A21, dot, 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 AM1. Plus, pull out the X sub 2 here. Why they don't put it on the other side, I don't know, but I'm trying to do what they do. A sub 1, 2, A sub 2, 2, dot, 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 A sub M2. Okay? Plus, and you keep on going. you hang till the get them all done. Do I need to do that last? I guess so. The last one is x sub n times a sub 1n, a sub 2n, dot, 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 a sub mn. Okay, now, and by the way, that is equal to the vector b. They don't list that out, but it is. Okay, now, why? What's the point here? Okay, well, here's sort of a point. If you called this first column here your a sub 1 column, this your a sub 2 column, dot, 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 all the way out to the a sub n column, then another way you could say that is, and I just don't have enough room to write, so I'm going to have to delete this and write, but hopefully you got it down. So your AX becomes a sub 1 x1 plus a sub 2 x2 plus a sub 3 x3 plus dot, 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 plus a sub m, I think it is, x, no, n, a sub n, x sub n, okay, and that's equal to your b, okay, so vector v. All right, so in other words, and these, by the way, are column vectors too. Now, I just realized that they put the x's in front. I still don't know why. It's okay. You can put them in any order you want to. But that gives you that. Now, then they go back and write the line they had above it again. And they say this is called that series of x of 1 times your a's plus x of 2 times a's, different a's. Okay. That's called a linear combination of the column matrix the column matrices are your A1, A2, dot, 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 up to A sub n, okay, with the coefficients and the coefficients are your x1, x2, dot, 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 up to x sub n. Okay. The x's are components of your, what you're looking for is a solution vector, you might say. Now, that matrix product AX is a linear combination of column vectors A1, A2, A3 that form the matrix A, and AX plus B is consistent if and only if B can be expressed as such a linear combination. Okay? It's consistent only if B can be expressed that way, where the coefficients of linear combinations of the system of equation. All right. That whole page just seemed like it was almost going in circles. What's the point in it? Okay, well, I guess it does have a point. We're going to do example 7 using that, and I guess we have enough time to get that done. here's a linear system of equations. X of 1 plus 2x of 2 plus 3x of 3 is equal to 0. Now, it looks like it might be a homogeneous system. It isn't, just that one equation. 4x of 1 plus 5x of 2 plus 6x of 3 equal 3. And 7x of 1 plus, yuck, can't get this to go away, there we go, plus 8, x of 1 doesn't look too good, x of 2 plus 9x of 3 is equal to 6. I believe it is, yeah. Sorry, my writing is getting worse and worse. My eyes are hurting worse and worse. All right. Now, they say let's write it the way we did just before. X of 1 times this vector, 1, 4, 7. Man, this hurts. Plus x of 2 times the vector, 2, 5, 8. Plus x of 3 times the vector, 3, 6, 9. And that's equal to 0, 3, 6. Yeah. Goodness. 0, 3, 6. All right. And this just sort of ticks me a little bit. Then they just make the statement. Using Gaussian elimination, you can show that this system has infinitely many solutions, one of which is x equal 1, x1 is 1, x2 is 1, and x3 is minus 1. Well, if we're going to do Gaussian elimination, why didn't we just set it up to do it? But they didn't, and they say that's the solution. Well, let's just see if that's the solution. What was that? 1, 1, minus 1. This would be 1 plus 2. Oh, and minus 3 is equal to 0. That works. 4 plus 5 is 9 minus 6 is 3. Okay? And 7 plus 8 is 15 minus 9 is 6. Yes, that indeed works. Now, we didn't do Gauss elimination, but we did verify that one did. Now, for all we know, that's the one and only one, but it's saying it's not. Okay? As since there's infinitely many solutions, this is just one of them, B can be represented. Now, B, remember, is this. This is your B here, vector B. Okay? Can be expressed as a linear combination of the columns of A. Okay? That representation of one column vector in terms of others is the fundamental theme of linear algebra. Okay? Now, they do all that, and they just go on to other stuff. And this is a good author. I like him in everything else, but boy, sometimes here it seems like he just gets off, well, let's do this. Okay, now let's go do something else. You know, I don't find it very coherent. He's a good author, but boy, there are places here. Now, they just end it there, and now they start talking about partitioning. And they talk about that and end it, okay? And there must be some hidden reason he's doing this, but it's hidden from me. I can't, I don't know. I mean, here he just does this. What if you have a matrix, 1, 2, 0, 0, 3400, and -1, -2, 2, 1. Okay, a fairly interesting sounding matrix. And then they say, well, what if we partition it this way? A blue line there and a blue line here. Okay? Fine. Well, one thing you've done, you've separated these zero elements all to themselves, but I don't know what else they've done with it. Okay? They've just done it. Okay, now, I said blue lines. In the book, they're blue lines. I did them dotted lines. I didn't change the color. Okay? So let's do something a little different this time. This time, let's partition it in columns. Okay? So that'll be a column, that's a column, and that's a column. Okay? And we're going to call these column matrices. C1, C2, C3, and C4. Oops. Okay. And again, why? Not real clear. Or, if that's not enough, we'll get rid of those again. Okay. And then we're going to partition this by rows. Okay. And this would yield you row 1, row 2, and row 3. Okay, sorry. And that's an ugly, ugly 2. I'm not always looking at what I'm writing, I'm just writing. Now these are also vectors. Okay. And again, they just leave it hanging and say, yeah, you can do this. I'd say, great, you can do this. We just did, so what? Now, linear algebra applied. I find this a lot more interesting, but we're not going to do it. But let's see. Many real-life applications of linear systems involve enormous numbers of equations and variables. A flight crew scheduling problem for American Airlines required the manipulation of matrices with 837 rows and more than 12,500,000 columns. Wow. This application of linear programming required that the problem be partitioned into smaller pieces and then solved on a Cray supercomputer. I think that's what they have up in Huntsville. Enormous computing capacity. Okay. Now there's a source there if you want to look into it and go write a paper using that. They give you at least one source that you can look at there. That finishes 2.1. Okay? Homework exercises here, and all these odds are at CalcChat. 1 or 3, both of them at CalcChat. Any of the odds, 5 through 11, they're all at CalcChat. 13 and 15 are at CalcChat. Any of the odds, 17 to 29, they're all at CalcChat. 31 to 37, they're at CalcChat. 39's at CalcChat. Any of the odds 41 through 47 are at CalcChat. Sorry, my throat's hurting. 49 and or 51, they're both at CalcChat. 53's at CalcChat. And 55's at CalcChat. Now, here is one other little thing that gripes me about this book. They introduce a fairly major concept in the exercises. Not in the text, but in the exercises. It's not a hard concept, it's just defining a diagonal matrix. A diagonal matrix is example 57 and 58. 57 is odd. Find the product AA for the diagonal matrix, and that means you multiply that by itself. And they give you a matrix. 57 is a diagonal matrix. Why is it diagonal? Because its main diagonal has entries other than 0, and all the other positions are 0. Why couldn't they have said that in the book? You know, it's a fairly major thing, but they did. Okay, then 59 is you making the products of diagonal matrices. Okay? 61 is a guided proof, and I bet you your previous instructor would have loved that one. So you can do it if you like. Either 63 or 65, they're both, should be at Calc Chat. 67 is another proof. It should be at Calc Chat. Oh, by the way, before you get to 63, there they give a definition in the homework exercises. If it was important, give it in the text. The trace of a matrix, the trace of an M by N matrix, A, is the sum of the main diagonal entries. Okay? Just add those main diagonal entries together. And then it says find the trace of 63 and or 65. Pretty easy concept, but why in the world wouldn't you do it? But then they just leave it there. They don't tell you why they defined it that way, how you use this, or anything else. 67 is a proof. You can do that. I'm sure you want to jump on that one. 69 and 71 and 77. You can choose any of those you'd like to do. They're all at Calc Chat. 75 is another proof. You can do that if you'd like. It's a Calc Chat. 77, you can do that one. That should be a Calc Chat. Then there's some sort of application problems, and you can choose any of these you want. An agricultural problem, 79. A politics problem, 81. If the politics isn't a problem enough, okay? Now, 83, here's some more definition, okay? They're talking about block multiplication of matrices. And here, finally, they show you something you can do with the partitioning they did back on after example 7. And they just said, hey, you can do this. But they don't say why you can do it or what to do with it. So now this is getting into sort of an application of that. So you can play around with 83 if you like. 85 is a true-false. This should be at Calc Chat. And then 87 is the last one. It should be at Calc Chat as well. Okay. So 2.1 were basically operations with matrices. 2.2 goes into properties of some of these matrix operations. Now, we've hit a few of these already in a sense, maybe not explicitly, but we have dealt with them. We've got just a few minutes. Let's just go over these properties, and they're calling this the algebra of matrices. So let me clear this off the screen and list it. It's in your book, but because not everybody has a book, I'm going to list these. So what we have here is capital A, capital B, capital C are matrices. Okay? And they're all M by N matrices. Okay? C and D are scalars. Any old scalar, positive, negative, fraction, decimal, rational, irrational, any real scalar. Then the following properties are true. We've already shown this one. A plus B, as long as they're same size matrices, you can add them, and they'll be the same result as if you did B plus A. And again, that's the commutative property of matrix addition. Okay? Number 2. A plus B plus C is the same as A plus B plus C. That's the associative property of matrix addition. Okay, get right. Now, 3. Kind of a weird little thing. CD, the product of C times D, multiplied by matrix A. C and D are scalars. Matrix A is a matrix, of course. That's the same as C times DA. All right? And it's sort of okay. Now they call it the associative property of multiplication. I think that's a little too general of a term. That's the associative, and this is way too specific of a term, property of two scalars and a matrix multiplication. Okay, maybe multiplication of two scalars and a matrix. That would have been a better way to do it. Two scalars and a multiplication of two scalars and a matrix. Because you can't just go and put in other matrices. That won't work, okay? You can't even do it, okay, necessarily. Number 4. And this is a piece of cake. The number 1 multiplied by matrix A gives you matrix A. That's the multiplicative identity element. Okay, multiply 1 by anything, it stays the same, whether it's a number, a matrix, or anything else. Now that's the number 1. You've already seen an example that the letter I works there well too, but they're not putting it in this table yet. Okay? Number 5. C times A plus B. Sure, you probably can guess what this is. That's CA plus CB. And that's a form of distributive property. And they just leave it like that, distributive property. But I like to say distributive property of scalar multiplication over matrix addition. Okay, a little more specific. And number 6 is somewhat similar. It's C plus D, the two scalars, multiplied by matrix A is CA plus DA. And again, that's distributive property of, this time it's scalar, really doesn't matter. You could say matrix multiplication over scalar addition is probably the better way to say it. I don't know, maybe this scalar addition over, I would say just multiplied by matrix. Okay. The thing is, you can split them down, do them however you want. Now, notice you can't necessarily do, in fact, you can't have a matrix out here if there's a matrix in here, okay? Nor can you do, if there's these are two matrices here, have a matrix out there. Just can't do it because these are m by n's, and they don't even fit to do that way. So you just have to watch them. They're sort of distributive properties, but they're very specialized distributive properties. Okay, I think we have run out of time. I'll let you do the proof at home, and if you're interested in doing that, we'll start next time with example 1, where we'll start applying some of what we just did. All right. Have a good weekend. Don't forget your research paper. And you also have your first test you're working on. So you got some stuff to do. What's that? You can turn it in today if you want to. Obviously, you're the only one here. So I'll take it if you want to turn it in. If you want to go over it this weekend, you can.
Do you take like partial credit for
Oh, of course I do partial credit. That's why they're all problems. There are no true false or multiple choice or things like this. That way I can give partial credit. Otherwise, that's yes or no answers, right or wrong.
to get all of them. So number 7.
Right.
I put down some answers. I don't know if they're right.
Okay.
But all my work for number 7.
Okay.
Separate sheet of paper.
That'll be correct. Thanks. All right, good deal. So give me plenty of stuff to grade this weekend. Thank you very much. Okay. All
I
right.
try to make everything good, so it won't be hard.
Right.
Alright.
That's the way to do is keep on top of it. Don't let it get on top of you. You'll never get out. Okay. All right. Oh, I need to mark the others absent. Gotten into a pretty bad pattern here. I appreciate your coming, but all week it's been just you. Okay. All right. We'll see you Tuesday.